What if you could breed AI agents the way nature breeds organisms? Instead of manually tuning prompts, picking models, and configuring tools, you spawn a population of agents, let them compete on a task, kill off the underperformers, and let the winners reproduce with slight mutations. After 50 generations, you have an agent that's dramatically better than anything you could have designed by hand. This is natural selection for AI agent development. And today we're going to break down exactly how it works, survey the research behind it, and give you a concrete architecture you can build. Let's start with the biological analogy. In biology, fitness is an organism's ability to survive and reproduce. For AI agents, fitness is a scoring function. How well did the agent complete the task? How fast? How cheaply? You combine these into a composite score. The agent's DNA is its configuration. The system prompt is a genome. Temperature is a phenotypic trait. Tool selection is an adaptation. Few shot examples are instincts. Memory architecture is brain structure. Everything maps cleanly. Mutation means making random changes when an agent reproduces. You might ask an LLM to rephrase the system prompt. You might adjust temperature by plus or minus zero point 0.1. You might randomly add or remove a tool. Occasionally, you swap the underlying model entirely. That's a rare, high-impact mutation. Crossover means combining traits from two successful parents. Take parent A's system prompt with parent B's toolset. Average their temperatures. Combine their few-shot examples. Selection kills off agents that can't compete. Tournament selection picks 3 random agents and keeps the best. Elitism always preserves the single best agent unchanged, preventing regression. Now let's look at the research history. Kenneth Stanley's NEAT algorithm in 2002 evolved not just neural network weights, but the network topology itself. It introduced speciation, grouping similar agents to protect novel solutions from premature elimination. In 2017, OpenAI showed that evolution strategies could match reinforcement learning on Atari and MuJoCo benchmarks while being dramatically simpler and more parallelizable. They solved MuJoCo humanoid in 10 minutes using 1,440 CPU cores. Google's AutoML0 in 2020 went further, evolving entire machine learning algorithms from scratch, starting with basic math operations. It independently rediscovered gradient descent and learning rate decay. Pure evolutionary search, no priors. Evo prompting in 2023 bridged evolution and LLMs directly, using the language model itself to perform mutation and crossover on text prompts. It achieved state-of-the-art results on prompt optimization benchmarks. And Evo Agent, presented at NeurIPS 2024, is the most relevant to what we're building. It uses evolutionary algorithms to automatically generate multi-agent systems from a single expert agent, with agents specializing into different roles through evolutionary pressure. The trajectory is clear, from evolving network weights to network topology to entire algorithms to text prompts to full agent configurations. Each step brought evolution closer to the abstraction level where modern AI agents operate. Now here's the concrete architecture. An evolution controller manages 4 components: a population manager, a fitness evaluator, a selection engine, and a reproduction engine. Each agent is defined by a JSON genome containing its system prompt, model, temperature, max tokens, toolset, few-shot examples, memory strategy, and thinking budget. This genome is its complete behavioral specification. The fitness function is the most critical design decision. It must be automated, multidimensional, roughly deterministic, and fast. We use a weighted composite: 40% quality, 30% completion, 20% cost efficiency, 10% speed. For selection, we combine elitism, the top 2 agents pass through unchanged, with tournament selection for the remaining slots. Bottom performers are terminated. Reproduction fills the population back to N agents through cloning plus mutation. The mutation rate of 30% means roughly 1 in 3 genome parameters gets randomly perturbed each generation. The generation loop runs this cycle: spawn, evaluate, score, select, reproduce, log. After 50 generations, the fitness curve typically shows dramatic improvement. Let's talk about real-world applications. Prompt optimization is the most immediately practical. Evolve prompt variants instead of manually A/B testing. Tool selection discovers which combinations work best for specific tasks. Memory architecture evolution finds whether RAG, sliding windows, or summaries work best for your use case. You can even evolve entire multi-agent team compositions, the number of agents, their roles, their communication patterns. But there are challenges. Fitness function design is the hardest. A bad fitness function leads to reward hacking. Diversity versus convergence is a tension. Without diversity pressure, all agents become clones of the first good solution. Compute cost adds up. 10 agents times 10 tasks times 50 generations equals 5,000 LLM calls. LLM stochasticity means the same config might score differently across runs. You need multiple evaluations per agent. And local optima can trap evolution, use adaptive mutation rates and occasional random immigrants to escape. To get started, define 5 to 10 representative tasks, design a simple fitness function, and start with just 5 agents for 10 generations. Total cost, $5 to $10. If the fitness curve trends upward, scale from there. You can implement this with pure Python and API calls, with OpenClaw subagents, with LangChain, AutoGen, or DSPy. The conclusion is simple. Natural selection isn't just a metaphor for AI agent development. It's a practical engineering strategy. The mapping is direct, the research validates it, and the architecture is implementable this weekend. Stop hand-tuning agents. Start evolving them. The agents of the future won't be designed. They'll be bred. For the full article with code, diagrams, and references, visit thinksmart.life/research. Thanks for watching.